how's everybody doing tonight? Okay. Thanks for all your emails. My wife is much better. She's had a kidney stone. She's got a hospital over the weekend, so things are going much better this week. So back to normal. Tonight we're going to be going over Chapter 4, TCP/IP. The lab we're going to do this week is setting up a LAN. Next week we're going to do the creating straight over cross cable, straight crossover cable. We've been reconfiguring this lab a little bit today, and so we're going to do the crossover cable next week. Do this now so we won't forget. In the week 5 lab, if you could submit your name, that'd be awesome. So again, next week, right when you come in, we'll go right into the crossover cable lab and the straight cable lab. It'll take our entire time to do that. Tonight, though, we'll talk about TCP/IP and then go right into the LAN. You should have at the end of your tables there a hub. This row here, the middle 2 rows do. I'm sorry, your row doesn't. We're going to do groups of 3 and 4, I think it is, for the lab. We're going to be setting up a small area network, which is one of the things you need to learn how to do in this class and learn how to do when you're in networking, so you're going to do that tonight. So let's get started here. Like that. There you go, that's better. Okay, we're going to look at what TCP/IP protocols are, and the model, how it correlates with the OSI model. We'll look at that, and then also 2 different versions of IP version 4 and IP version 6. And we're going to end on subnetting, just the beginnings of subnetting tonight, and then we'll go right into the lab. We'll look at DNS, basically the purpose of it, why we need it. So, characteristics of all TCP/IP, and it stands for Transmission Control Protocol, Internet Protocol. It's a suite within computers, regardless of what type of computer it is today. It could be a Mac, PC, Linux. They're all going to have this suite of protocols, IP and then TCP. Sub-protocols to this suite is TCP, IP, UDP, and ARP. In the PCT130 class tonight, we actually did what's called ARP poisoning, which you take and you poison the ARP table to let the server think that a computer is the actual server, like this laptop. In ARP poisoning, a hacker will take a laptop like this and set up ARP poisoning and redirect all the traffic on the network to this laptop to gather data, whether it be passwords, whether it be user activity. In the lab we did earlier, we set up a man-in-the-middle attack where there was that computer actually there that was the attacker, and it was had a spoofed Facebook page, Facebook site using XAMPP on that machine. And then when the students came in, they logged into facebook.com on their machines. I had them log in bogus username and passwords, stop the attack, have them come over to this machine, and showed them how all the data that they entered in, username and passwords, was collected by this machine. And that was all done by ARP poisoning. And so ARP is just one of the suites in the protocol suite. It was developed in the 60s by ARPANET, the actual TCP/IP protocol, for security purposes, for communication purposes. It was a precursor to the internet. It started in the 60s between multiple universities and governmental bases. Advantages of TCP/IP is it's open in nature, it costs nothing to use, And like I said, all OSs use it now. Now, when Apple first came out, they had their own Apple Talk years ago. They dumped that, and now for years have only used TCP/IP. Same with Linux; they've always used TCP/IP. So it's cross-platform, costs nothing to use. It's flexible, runs on virtually any platform, even mobile. It connects disassembler operating systems and devices, regardless of the flavor of operating system. They'll talk just fine to one another. It's very routable. You could take a Cisco class here. It's an 8-week class. It teaches you how to do routing with IP addresses, and real important to know how to do that if you're going into networking. And transmissions carry network layering address information across the medium, whatever that medium might be. Cat5, which we have here on campus, fiber. Suitable for larger networks because it's routable. You can subdivide it using subnetting. So you could have a subnet for, say, voice, a subnet for data, a subnet for Wi-Fi, we'll say, to be real simplistic. And you can set up your network and segment it. That way, if an attacker was also to come onto your network, if it's subnetted into multiple subnets, they might be able to attack one segment of it, not the entire network. And so that's beneficial also. The model of the TCP/IP, it's 4 layers. It falls upon the OSI application layer, transport internet layer, and a network access layer. So this is what it looks like as far as the model corresponding to OSI. OSI is there on the left, on the right. And in the middle is the protocols, and on the left is the different TCP/IP protocols. So you've got TCP/IP and the model, OSI and the model. The TCP/IP model application protocols on that would be HTTP, FTP, Telnet, NTP, DHCP, and ping. OSI equivalent falls in the application presentation and session layer. For the TCP/IP model, transport falls in the TCP/IP and UDP, or TCP and UDP. It's also in the transport on the OSI. For TCP/IP model, internet falls in IP, ARP, ICMP, IGMP, and it's in the network of the OSI. And then the bottom one is the network access. This will be the physical link layer of the OSI model, and it's where the physical cable plugs into your NIC card. So corresponding protocols are fairly similar to OSI, and then the middle is all the different protocols that is a part of the TCP/IP suite. And you've probably heard of most of these. HTTP, I know you've heard of. FTP, you've probably heard of. Telnet, maybe not. NTP, DHCP, you've probably heard of, where that's a component in the protocol that casts out the IP addresses to the network machines. Ping, went over that already, where you ping an IP address to determine if it's up or not, if it's alive, and how long it takes. So the sweep sub-protocols basically all function in the transport network layers of OSI. They provide basic services for the network to work, basically. And the 2 protocols that we're going to play with tonight, we play with mostly in networking, is TCP and IP. IP in and of itself is kind of open, no rules. TCP is a part of the wrapper around IP to create the rules so it'll function properly. So making sure data gets there, checksums. So if a 2 meg packet's sent out, the 2 meg packet makes sure it gets there. That's all done in the TCP part of the protocol. So the transport layer protocol provides, again, reliable data delivery services. It is connection oriented. It must establish a connection before anything's transmitted. It uses checksums and sequencing. Going back a few weeks, we talked about the caboose of data being broken up into multiple segments, and each segment being like a caboose on a train. That's the TCP portion of it. It keeps track of all that and makes sure, even though things are segmented out, as data goes out, it brings it back in the order it was thrown out, from 0 to whatever, and make sure it's all there. If one IP packet's missing, It'll tell the router to resend it again until it's all complete. It also provides flow control, segment formatting, meaning it just encapsulates every IP packet with like a network address. It packages it with that network address, and that network layer address could be more than likely it's going to be a source IP, destination IP, MAC address of both where you're at, where you're going. So if you're on a computer and you're clicking a link on a web server, it knows your MAC address, it knows that web server's MAC address. That's all part of that packaging. So you have here a blown up TCP segment. You'll notice at the very top, you've got the source port and the destination port. All right. If you're talking about web, your source port could be, say it's 84 through 39. And your destination port on a web, clicking on a link would be like port 80. If any web page you click on is going to have port 80 for the web server to work. The local source port can change though a lot. Just depends upon when you click on it, what open port your computer has. It doesn't really matter to the computer, by the way, on that source port. Destination port though, for the most part, is going to be port 80. It could also be, if it's a secure connection, port 443 for SSL. So if you're connected to a bank account, it could be port 80 and port 443. FTP, port 21, port 80. And so all these different ports can change on the destination, but port 80 generally will be your base port, if that makes sense. Port 80 is going to also be always be anytime you deal with a web server, it's going to be a part of it. Sequencing number and then acknowledgement basically attaches it to that IP address. You've got the header length. These here, the URG, ACK, all the way to FIN, those are actually from long ago, whenever we had dial-up and we had analog, and on the modems, you'd actually see the lights with these acronyms on the lights, and it was basically for handshaking. It's still in the protocol. The two that's used the most in here is going to be synchronization, SYN, and the FIN, and acknowledgement, third one. It's going to be used as well, acknowledging that packet. The rest of them aren't used so much anymore, but they are still in there in the header. The sizing, window size, has been the same. It's usually like a 5026, 5036, 5096 size window, and again, that goes all the way back to DOS days. When packets were sent, all we had was working with a black DOS application. That's not changed, but it's still in there. It's not going to hurt anything. It's still in there. Checksum and urgent point, though, these two check to make sure the data, when it's created, creates a checksum on the source side. The destination side makes sure that checksum matches, and that's going to be a lot of times an algorithm the network creates to create that checksum, along with the data size, dumps it over on the other side. They check it as well on the router on the other side to make sure it matches. Then there's options and padding. That row here basically deals with, say, time to live is an hour on options. It could be in here, the options. Or connections is an hour, and that's it, and it's done. And then finally, the last one, data. Data is actually what you're sending across the path, what you're sending across to the other side. So you've got basically in this one, the source port, the destination port, all of the different flags that it could adhere to. And basically all you need to know on this screen is on the flag one where it talks about URG, ACK, PSH, RST, SYN, and FIN. These are all, again, built in years ago, a collection of flags to determine collision, urgency, if a data is finished or not. Checksum, allowing receiving node to determine whether the TCP/IP segment became corrupted during transmission. So if there's a man-in-the-middle attack or whatever, that would be found in that checksum. Here is a segment data breaking down the actual data itself of the TCP port part of the segment to determine source port, destination port, sequencing number, acknowledgement number. And you'll notice the source port here is port 80, destination port 1958. As a sequencing number it gives it, acknowledgement number it gives it, the flags, window size, that 5,000 number. The option on this one is 4 bytes per data packet. So TCP, the segments here are established in the connection. Oh, are you smoking out here, by the way? Yeah? Yeah, don't do that. Sorry. So the segments basically have to do with, you've got 2 connections that come with the TCP. You got computer A, say, over here, computer B. Computer A sends a message, right? Computer B receives a message. When the computer A sends a message, it's going to send what's called a send segment, which is basically just data with a signal out that has some number, a random number that the computer creates in the network. Computer B receives it, and then after computer B receives it, it tacks onto an acknowledgement field, recognizing it, that yeah, I received it, +1 it says here. And all it's doing on this one is adding to that an increment of +1. And so say, for instance, a time to live was an hour. It's going to know after a time, if it didn't complete in an hour, to resend it. Or say it was 10 minutes, or say it was 15 minutes, or whatever the case may be. Like back in dial-up days, you guys remember dial-up? When I lived here in Rockford 20 years ago, no, not that long ago, 15 years ago, we had dial-up. And remember when it connected, it made that shriek sound. Make the shriek sound, and then, the handshaking would occur, and then it would connect, and then the dial-up service I had, I believe, was Earthlink or something like that, or no, Net Zero. Net Zero would then time out if you had no activity after about 10 minutes, and that's where it would, in this, or if I was downloading a file, say, and wasn't touching the computer, even though I was downloading a file, it didn't see that activity sometimes, and it would time it out and disconnect. And so sometimes you have to move the mouse or something like that to keep the connection alive. So anyway, it's the same technology we had now that we had then. The difference is we have faster modes of communication. We just got rid of our dial-up modem here on campus. We had 1 or 2 left that faculty were still dialing into, believe it or not. Last semester we got rid of it. Now those are out of the building, and they were in the IT rack somewhere back there. Because when I first started working here, you could dial into it and get internet connection for free if you wanted to. But the connection was so slow, you dial into it, get connected, wait about 30 seconds, then you'd have internet, and then you wait another 30 seconds to even have a web page load, and then maybe wait another 2 or 3 minutes to get another web page to load. So that's how slow it was. So basically, in TCP, it's finding the package, synchronizing it, acknowledging it, and then receiving it. Computer A then responds after A and B goes back and forth. A then responds, sends a segment number back to B, another random number, and finally the finished transmission flag is sent, and the transmission's ended. Now, that can be for, back in dial-up days, it was connect, disconnect, but today it's literally downloading a file, completing downloading a file, sending a file, the person receiving a file, things like that. Because most computers now are connected 100% of the time, even if a person's not using them. They're connected to the internet, connected all the time, flowing, data's flowing all the time. So basically, it's how it happens visually. You've got computer A and computer B here. 1, it requests for connection. It has a sequencing number goes across. 2, response sends that sequencing number back to B. A acknowledges it. And then finally, the connection is established. And whether it be for data, whether it be for connection of flow of data, whatever it might be. Then the UDP. This is a part of the package protocol that's part of the transport layer protocol. And it's a user datagram protocol, provides unreliable data delivery services. It's connectionless on this one. No assurance that packets will be received in correct sequence. No guarantee packets will be received at all. There's no error checking in UDP. It lacks sophistication, but more efficient than TCP because it doesn't have any rules. And so because it doesn't have the rules, it's used a lot of times for great volumes of data, transferred quickly. FTP uses this a lot because when you're using FTP, whether you're uploading or downloading, you're just moving data. You're not doing anything else. There's no other communication happening. Or let's say you guys might have heard of BitTorrent. BitTorrent files uses UDP protocol as well. It's faster, less protocols are tied to it. It's connectionless, but it gets the job done. Yeah, internet radio uses that well. Any media uses it, like streaming radio, streaming movies. Netflix would use it. What's another streaming movie thing? Netflix, Hulu, Amazon. Amazon got a streaming thing, I think. So any streaming media would work, would use this. And you'll notice it's a much less complex packet. You've got source port, destination port, length checksum, and then two data rows, and that's it. IP. On the video we saw, it talked about the IP being like the Wild Wild West, I believe, and that's really what it is. Just open. It's how and where data is delivered, though. Back when ARPANET first started, all they had was IP. There was no wrapping around it. There was no TCP. It was just getting data, typing something, and one university and the other university receiving that. That was big. That was huge. Even if it's just 2 or 3 letters. Enables TCP/IP to enter network. It transfers more than one LAN segment on IP, more than one network type through a router, and the network layer data formed in a packet. So the IP packet itself has an envelope, kind of like a caboose of a train. Contains information for routers to transfer data between LAN segments, and that information generally on IP is just the IP address itself, the source and destination. 2 versions. You've heard of version 4. That's the one we have now currently that most all computer networks use. It's connectionless protocol, unreliable in the fact that it's limited in its scope. And version 6 is the next generation, released in '98. All of your NIC cards have this capability now, and all networks can use it. Provides billions of additional IP addresses to the IP ranges, and there is better security and prioritization that's given in IP version 6. Version 4 packet looks like this. One thing I want you to just highlight on this one is version on the top left, then also time to live, second one down from that, source IP, destination IP, and data. That's the main part of an IP4. So again, version, time to live, source, destination IP, and data. 6 header packet, you've got version still, but notice, as we go back here, time to live's gone, protocol still in there, is gone. So you got version. Instead of protocol and things, what they have in this one is called traffic class. It's kind of like the way this is going to be designed is this. The way it is designed is, okay, anybody here been to Boston before? Been to Boston? Okay, well, I went there years ago, and they were building an underground transportation area, all underground. And the reason for it, they did it for like 15, 20 years. And the whole reason for it was they were going to have emergency on one level and then commuters on the other level. And I believe the emergency was going to be on the underground level and the pedestrian on the upper level, like the ground level. Well, same here. The purpose behind the traffic class is there can be segmented different levels of classes beyond what we have now in networking, to where you could literally use a class for, let's say, governmental, military, as an example, and then maybe one for commercial, one for whatever. The other one that's different is the hop limit. The hop limit in IP version 4, they had time to live. Time to live would be the equivalent to hop limit. Time to live would be 256 hops before it dies. Hop limit, same deal, just different name. Source address and destination address are the two big areas in IP version 6. It's in version 4, but version 4 also has some options, some padding, checksum, fragment offset flags, total length. It doesn't need that. In fact, some of the ones here in 4 were years ago when networking first came out, and it's no longer used anymore. So version 6 stripped all the stuff that's no longer needed, which gives you more addressing and more protocols to use. Internet Group Management Protocol. This operates on the network layer of the OSI. Multicasting for this one. Multicasting, anytime you hear multicasting, is generally going to be audio or video transmission across the lines. And it manages multiple multicast on the network running IP version 4. Point-to-point transmission, one node sending to many nodes, used for internet teleconferencing like voice over IP Cisco, video over IP, and Skype would be an example for maybe what you guys have seen, FaceTime possibly as well if you've used that. Then ARP table, address resolution protocol, the one I talked about before we did tonight in PCT130. It uses the network layer protocol, version 4. It also is on version 6. What it uses is a MAC address of the host or node in the network, creates a database and maps everything, maps the MAC to the host IP address. And so everybody in here, whatever your IP address is, you also have a MAC address on that machine. The ARP table has information about that, and it knows right now where everybody's at. It's saved to the computer's hard disk and increases efficiency because it doesn't have to look every time. It knows from the table. And where the poisoning comes in, I talked about earlier, is where you can run software like Cain-Enable that will poison that table to do, for hackers to do malicious activity for a moment, and then release that poisoning back to what it originally was. So it's harder to be recognized on networks, harder for the hacks to be recognized. ARP tables are fairly easy to hack. They are. You can, though, to harden an ARP table, you can do what's called hard code it, meaning I can hard code an ARP table and say this is a server's IP address and this is a server's MAC address. It will not change. Because ARP poisoning, what it does is it says, no, I want to change that to become the server. So it takes the MAC address of the server and poisons the ARP table to say this is now the MAC address of the server. And so by hard coding it, you can stop that from happening. Then Internet Control Message Protocol, basically on this one deals with time to live on the network. It also deals with transmission failures being announced and network congestion. So it's constantly telling the network if there's congestion, if there's failures on the network protocol table, on data as it's flowing. IP4 addressing has two addressing, logical and physical. The logical's on the network side, the physical's on the MAC physical side, MAC address, hardware, NIC card. It is 32-bit numbering. It's 4 octets. Each octet is separated by a dot. So you say like 192.168.1.1, or like this example, 144.92.43.178. Its network class is determined by the first octet in the network, and we do a subnetting here this semester where you'll learn how to find out what class it is by that first subnet in the IP address. In fact, here's a screenshot of it. You've got class A is, if the first octet is 1 through 126, it's class A, B 128 to 191, and C 192 to 223. You might notice that 127 is not in that second column. That's reserved for local loopback on your network. To test a NIC card's health, you're going to do a 127.0.0.1, and that's going to you do local loopback, or you can just do local host on a computer's browser, and this will basically show you the health of a NIC card. If you get full responses back, it's a healthy NIC. Otherwise, it can be having some problems. Class A, all I'll tell you on this tonight is Class A is generally used for local networks behind a firewall that does not really need internet connection. It's internet connectionless. It doesn't need it, but it does need connected one to the other. Class B and C is generally going to be where you have local internet plus some type of modem connection to that IP address to give internet connection. An example would be most of your home routers are going to fall in the B or C range. Depending on, like, AT&T starts with a 172, then I think you have like Cisco 192, and so B and C range is generally we're going to have a home. Here in this classroom we have a 172, but you might see networks that start with 10, like 10.1 or something like 10.1.1.1, and those can work fine. And you can still have internet on those. The difference is, you'll find out this semester, is you have to actually put in there what's called the DNS, and that DNS is then connected to the internet, and that's how that network gets internet. So Class D and Class E are very rarely used or never assigned. Class D is values 224 through 239 for multicasting. Class E is 240254 experimental. There's 8 bits. 8 bits have 256 combinations. Networks 1 through networks 254. 0 is reserved as a placeholder, and 255 is reserved for broadcast transmission only. Don't want to go over this one tonight on subnetting. Nope. I want to get into, because we did all this on our subnetting exercise. I want to do that. Okay, let's get into the sign IP. How many has a website, or you've developed websites, or you've played around with websites in the past? Okay, so you probably had some experience with registrars, right? Like GoDaddy or something like that. It started way back when that the government saw the need for some governmental entity or some entity to govern IP addresses, because there's only so many, because the growth of businesses wanting websites was growing. You had to have not only a domain name, but that domain name has to be attached to 1 or 3 IP addresses, 1 to 3 IP addresses generally that can be attached to, and then that's that company's or that business's IP address. It's just like a social security number, or it would be like a VIN on a car. It's tied to that company now, and hard coded for that company to use. Comcast here locally, if you're a business, you can buy Comcast for business, and you can get up to 2 or 3 static IP addresses for your business to use for web server, VPN, things like that. But the government-sponsored organizations dole out IP addresses. IANA, ICANN, and RIRs. Companies and individuals like us, we obtain it from ISPs, like we might get an IP address from Comcast or Verizon or AT&T. Every network node, though, must have a unique IP address from your computer on the network to websites on the internet outside of our building. Have to have a unique IP address. Static IP addresses basically is where you go into your TCP/IP on your network NIC card. We're going to actually do that tonight in just a few moments, and manually assign an IP address to every NIC card on your network to talk to one another. That's if you do not have a DHCP server, you have to do it that way, because the only way for you to have a TCP or an IP address is either manually put it in or be connected to a server that can give you an IP address. And when networks first started out, there was no such thing as servers, so we would do what we're getting ready to do tonight, which is basically connect computers, 2 or 3 computers, to one dummy modem hub, is what they call them, dummy hub, to connect one to the other. Just to make sure they're in the same IP family, and it works. So static. The next is dynamic IP addressing through DHCP. This is assigned automatically. Most DHCP servers have a lifespan for the IP address. So say you might have a lifespan of 48 hours or 1 week or infinite or whatever the case may be. Most likely, most of your IP addresses at work and home pretty much stay the same on your laptop and your mobile devices and stuff. They probably rarely change, if at all. Because once it sees you, it creates that ARP table on your laptop or on your desktop. And unless there's a conflict or there's something that goes wrong, there's no real reason to change it, right? Now, if you were to, say, reformat your hard drive and put all new software on it and reconnect your network, it might give you a new IP address, okay? But again, it could give you the very same one you had before. And so, but they are dynamically assigned to you on a DHCP server. It assigns it automatically. Our Microsoft server class teaches a little bit on DHCP. There's whole Bibles on DHCP on setting up networks using DHCP and also using, setting up a server to not only cast out IP addresses, but to set up rules per machine. But DHCP just basically has a pool of IP addresses you put in there in the server, tells what my range is that I can give out, how many. Same with your Wi-Fi routers at home, do the same thing. It reduces time for playing IP addresses, reduces potential for error in assigning IP addresses manually, enables users to move from workstation to printers, making IP addresses transparent for mobile users. And part of DHCP, real close family anyway, in Microsoft would be Active Directory. And Active Directory works in close proximity, to DHCP, and we do offer an Active Directory course as well here on campus. DHCP, basically, device borrows an IP address for a while on the network, has a lease time of whatever is set up by default. If you don't touch it, it's usually 48 hours. But again, that usually never changes unless something conflicts on your network. Configuration, specify a lease address range, configure lease duration, several steps to negotiate the client's first lease. You usually have to log into the client as an admin, connect to the network, then it sees you, then it assigns you an IP address. So we have here an example of DHCP leasing. We have one, the client A, what IP address can I use? And we see here number 2, the client A, use 123.45678 as your IP address from the DHCP server. Client A, I will take that number as my IP address, and then the IP address is now assigned to client A. And so the process fairly quickly done once they're logged in and registered as a computer in Active Directory, then they can assign it an IP. All right, that was pretty quick, right? Now, we've got 2 rows that have, who was it I put the modems on, or thank you. So what we'll do is this, we'll have you over here if you don't mind, and then 4 in the row there because I have more room to plug stuff in. And this will be pretty quick and painless, I'm hoping. And let me see, did everybody get a handout? Okay, so get in your places, and I'm going to go over this real quick and then let you go at it, and then we'll be done. So here we go. This lab shows you how to set up a local area LAN, local area network using a hub, like this gentleman has here. Hub, 3 straight cables, and you guys should have 3 straight cables on your table, hopefully, and then 3 PCs. Now, your PCs are currently connected to our network here in the class, so you will have to unplug in just a second from the back of the PCs the existing connection. I'll move this away from you guys. So there are little drawers on the back of these you guys will have to bring down to unplug your connection. Take it back. They have these on the floor now, so you won't have to do that. They're on the floor, so you can do that in just a second. So let's just go over this real quick, and then I'm going to let you fly at it. So you need at least 3 PCs on ports 2, 3, and 4 on the hub. And the reason I want you to use ports 2, 3, and 4 on the hub is port 1 is generally used for an uplink to another dummy hub. So we're going to use ports 2, 3, and 4. You're going to set the IP address manually. So let's just go ahead and number everybody so we'll kind of know who you are. I'm going to have you be 1, 2, and you 3. Okay? And then computer 1, 2, and 3. Even though there's 4 in this group, well, that'll be the numbers. So what you're going to do basically is set up the IP addresses first manually on each PC. I'll walk you through how to do that using network connections on your computer. You just go to Start, Control Panel, Network Connections to get to it. If you need help, I'll come around and help you. And basically on B, 2B, that's how your connection is going to look like in the IP protocols. So this one's 10.0.2.1. If you hit the tab key right after that, it'll fill in that 255.0.0.0. You do not need a default gateway for this to work. All right. Keep flipping. You'll do the same in PC2, PC3, except you'll add a different octet on the end. Will be a different decimal number for each one of them. Then once you've done all that and everybody's connected in to the hub, because what you're going to do is on ports 2, 3, and 4, you're going to put your Cat5 in ports 2, 3, and 4, plug this into power, plug the Ethernet into your PCs, do these steps we just went over, step 2, where you're setting up your IP addresses. Then on step 3, by that time, it'll recognize everybody, and you'll be able to share folders from your desktop and see each other. That's step 4. And follow the steps in step 4 on sharing and security. Step 5, you'll browse out to see each other. Make sure on step 5, where it says A, do a Windows E command. The Windows button on your keyboard is what's that referring to, and the E button will open up Explore. And do a / 10.0.2.2.1 or .3, depending on your computer. So .1 computer will say go out to .2. .2 will go out to say .3, 3, 2, 2, 1. Right? So you guys are going out to different computers while you're doing the lab. When you connect to that person's computer, you're going to create a text document with your last name, first initial last name. Type in your first name and last name into that document, save it. And when you're done with it, all I want to see is you don't need to upload this file. I just want to see that on your desktop is that file that each other you created on each other's desktop. Then when you're done, what I'm going to have you do is delete that folder. We're going to reset everything back to auto-config on TCP, and then we'll be done. Okay? So the first thing you guys need to do is plug in your hub and get your connections, your Cat5 connections from the hub to the PCs. Get that done first. And there should be power supply over there too, I believe. If not, let me know. You guys should have power supply around there. And if you need help, let me know. Definitely help you. Oh, I'm sorry. Here, I'll take that. Out of your way. Don't need a black easel.